Good morning. Thanks for the introduction. Today I'm planning to tell you about service-oriented governance with service programming language. What is governance? In general, governance is the set of rules and laws framed by the government in politics that are to be implemented through the representative of the state. Simply put, governance is what governments do, basically, okay? So, in service-oriented computing, governance is service-oriented process expression, and as you know, the computer science is the science of process expression. So, if we talk about service-oriented computing, we assume that everything is service, like in object-oriented programming, everything is object, like in procedural programming, everything is procedure. As in functional, everything is a function. So normally you cannot find formal definition what is service, and basically there is no really service-oriented systems except what I'm doing over past 20 years in many different organizations. And government, in the context of regular concept of governance, is service-oriented process actualization, which is normally in computing operating system. And representatives of the states correspond to service-oriented processor, which is in service-oriented computing is the network of services. So all services in service-oriented computing are not available directly, because if they are available, they have static connections, network will break. There is no network really, it never will be completely secure and reliable. Because of non-reliable network, if you want to have reliable service-oriented computing, you need non-direct communication. That means consumer of service never talks directly to the service provider. And it is really difficult to achieve. And that's one of the major problems why service-oriented computing is not widely used yet. So service governance is defined by rules and patterns of service composition and an execution platform. And I'm talking already for a long time about Sorcerer, and Sorcerer is like, you know, any other good programming environments like Java. When you say Java, for some it is just coffee, okay? But for some it is object-oriented platform. For some, within that platform, they don't think about platform, but when you hear Java, I do Java program, this language basically, okay? And Java itself is operating system. Operating system that uses basically virtual machine with own file system, all virtual machine modules and so on. And obviously Java is also philosophy. It is object-oriented philosophy. And the same we do basically with Sorcerer. When you hear Sorcerer, it is service-oriented computing environment. My colleagues at General Electric Research and Development Center came up with that idea. By the way, I teach only in Polish-Japanese Academy of Sciences once per year for 1 week, and the rest time I work in the States. And initially I came for 1-2 years. I'm already working for 30 years, so I am almost all the time there. So in Sorcerer is philosophy, it is computing platform. It has language, service modeling language, it has obviously network operating system. And usually when I talk about Sorcerer, I talk about one of those components. And today I'm trying to basically talk about service modeling, service-oriented mogramming language. You tell mogramming, you will soon learn why we are talking, but mogram is either model or program or any combination of models and programs or anything else, okay? In the past, we assumed that model is conceptual definition which is not executive. Currently, we run models basically as executive entities, and usually model is declarative, while program is imperative, okay? That's the reason in service, when you create governance all computing paradigms, and that's the reason I use a term mogram, and language is mogramming language. So, why you need service governance? First of all, it is not a buzzword for doing computer client-server computing or any web services, okay? We tried that for many years. When I came to the States in 1989, we worked on $100 million project funded by DARPA, DARPA Initiative in Concurrent Engineering. I have some data here. We tried basically to do service-oriented computing 30 years ago. And as I told you, $100 million project. And it was to some extent successful. We applied to G90, the General Electric engine that runs on Boeing 777. Okay. Then basically I work on FIPER. That was my project for $21.5 million, Federated Intelligent Product Environment, that was funded by NIST, National Institute of Standard and Technology, to develop service-oriented technology. And then I continued basically research at Sorcerer, where General Electric founded the laboratory for service-oriented computing, Texas Tech. And during 8 years, we developed basically operating system that Air Force Research Lab started using in production for designing new generation of air vehicles. And as I told you, I teach basically service-oriented computing systems and software engineering design to create service-oriented computing system. And here basically, not everyone needs service-oriented computing. Service-oriented computing is for large, complex, adaptive system where you do computation or design with millions of billions of variables, okay? And you have to do this on the network. You use basically all computing resources in the network, supercomputers, clusters, workstations, because the number of variables is huge and the processing power is enormous, because you don't want to design, let's say, geometry and make a plane. You want to fly the plane virtually and check all parameters during flight virtually before we will go and start making a plane, because I don't have the slide, but that is interesting slide. DARPA asked for research why planes like Osprey or F-35 are basically from original design to introduction into practical theater. It takes 25, 26 years designing a plane that it is used. There's enormous amount of money, and the government said no more money. You have to do basically design using high fidelity physics. Because why they do design so long? Because those planes break. Because if you use those empirical formulas for designing, they have error up to 20, 30%. And when you design, then you fly and it breaks, it breaks, it breaks, it breaks. So they started introducing high fidelity physics model, but that's huge compute power basically. And basically appropriate languages are needed. So that's, and I forgot to mention, a year ago I was talking here about Sorcerer, but in the context of emergent, that was the title of my presentation, Emergent Multi-Fidelity Service System. Basically, we are looking, the topic was basically on the issue that if you run computing and basically optimization of very complex system, you want to observe emergent behavior and acquisite knowledge, learn and build new theories about how to build a thing that you are really optimizing, okay? So it is basically a kind of knowledge acquisition in very large systems. But today I want to be focused more on language, which is process expression. And as you know, there are many ways to express processes, and there are many different types of processes. When I was here, many presentations have been talking about only algorithms, algorithms, algorithms. Algorithms is very narrow class of process expressions. Okay, most processes are not algorithms, just my comment. And service-oriented computing is not algorithmic. You might use algorithms, but in general it is not. Object-oriented programming is not algorithmic unless you use object-oriented programming only for procedural programming, which is, in most cases, people are not aware what is object-oriented programming. They use object-oriented programming languages, but they write algorithms, basically. So this is the summary, basically. So you have basically domain. You want to create basically different types of analysis. You have to express those processes, for example, design processes, optimization processes, exploration processes, parametric analysis, and so on. And basically, you don't want to do this in software languages because the number of programs already written is thousands, okay? And which program to use when it is not clear and it is not easy. So engineers don't do this normally because that stuff is written mostly by programmers, software developers. So the concept here that you use basically executive codes that can run on many different platforms in the network, really. And you have operating system then basically uses domain-specific languages like service programming language. I will show you how it looks basically later. And basically operating system allows you to use executive codes as basically service avatars. I hope everyone has seen the movie Avatar. So basic codes that everything we write in software engineering becomes software avatars for softwares which are used here. So software is programming language for governance is not really executive code. It is called governance. It basically specifies how to use executive codes. Okay? So, and this is part of the, it is just language, the new term used in computer science, language engineering. So I am focused basically on language engineering for service orientation. And that's basically where it is applied. You have a lot of new concepts like we need in programming a discipline, we need in programming couplings between disciplines, we need in programming multi-fidelities as first-class citizens. Not using some objects, but you have those domains more in service sense, functions which bind to those service avatars codes somewhere in the network. That was what I was trying to explain a year ago, basically. So I will skip this, that emergent behavior with multi-fidelity managers, which is a really powerful environment to basically acquire knowledge and form automatically new theories about design. And that's what I'm trying to emphasize today, that we are already for a long time in service economy, and the change really is reinforced by economy. So if you look here at the picture, today's services sector makes up to 80% of US economy. 80% that service. Companies like General Electric, even when I joined in 2002, General Electric Research and Development Center, at that moment, General Electric was making 50% money from services. But before it's completely manufacturing company. Okay? So you see that increase is 500% in services currently, basically. So, and manufacturing is decreasing. So the value of products decreases, and we move basically into services. Why that happens, basically? It is related what is called in economy product dominant logic, where production is the core of value creation process. So you have basically producers, and the value is in the production. You want to basically produce as much as possible, possibly mass production, as cheap as possible, and distribute to customers. And with that idea came, as you know, Ford with Model T, and he was assuming that if he will produce cheaper cars, everyone can buy and market will be running forever. But currently, markets are saturated with products. It is not so easy to sell products, and what economy is doing? Creating services for those products. That's the reason we have a service economy where the focus is shifted to services, okay? And that's the second part. So this is the standard process. Also in software engineering, we are changing and we want to do what is economy already doing, basically. We try to do all those business like General Electric when I worked, they try basically to provision those products and make services. Like General Electric, I don't know if you know, makes aircraft engines, but they are not selling engines. They have GE Capital, and GE Capital takes those engines and leases those engines, basically a service. So they get money, really not selling engines, but providing services. Engine becomes as a service, okay, like a car. If you look in the car is just avatar, physical representation of the service, which is really service of moving us from A to B. That's the reason, you know, like in New York City, it doesn't make sense a car at all, because for parking, you pay per year more than value of the car, okay? And on the top, you have to pay insurance, you have to pay for maintenance, you have to pay for gas. But doesn't make sense, basically, to use product as customer, because other services related to car are so expensive with respect to car that it doesn't make sense. What happens? You know, Uber, okay? And you have that possibility. You take iPhone, basically, you click on Uber, that's the service. Uber uses mapping service. You have a map, you have GPS, okay? And then basically, you have cars displayed. You point where you want to go. You have car displays as basically basically avatar, okay? And then you select the car, and car comes, and you pay for a ride. Okay, and you know probably that Uber is investing heavily in the States in self-driving cars, so they would need, even in the future, no drivers would be needed. And cars go away as a product they will be buying. That's the service economy. And the same, we apply already, we started applying, that was the concept basically, because service economy, software development. We want to use software basically as basically a product. That means we want to basically, this is current predominant software development process. You have software development process and you create software artifacts, executed codes, which are products. And you basically sell, distribute to customer. But in service-oriented computing, we don't use term customer, because those products are custom products that user cannot change. So we want basically design, for example, designers who design plane or design any very complex system with high physics, basically physical, with models based on high fidelity physics. They basically use a lot of the ATUs, application to utilities, okay? This is the avatar of the services, physical representation, what they want to use here, but how to connect and use them, engineers know very well. They don't have currently tools, possibility to integrate hundreds of thousands executive codes into a code, because normally that integration is done by producer. I jumped too quickly. Anyhow, so basically in service-oriented computing, the consumer basically is co-producer of the, let's say, product, because it uses own knowledge, and the value in service-oriented computing shifts from the production process to the basically co-production by the end user. End user is becoming co-producer in terms of application tool and utilities so spread and used in many ways. Like when I started working on 5P project, General Electric aircraft engines, they had 30,000 programs, okay? And they know what best tools are for what processes, and they would like to eventually, in uniform way, to create service governance, how to govern those executive codes, application tool utilities in the network, including basically provisioning. Provisioning is the toughest part, basically. That's the reason it have taken us so much time, because those application tools and utilities, they are not in the network all the time. When you create your governance, the governance includes deployment. So they are provisioned on demand when they are needed in the network. You finish your computing, they disappear from the network. So they are not servers. And that's an illustration also that we are moving from few node systems, like those are servers, and they have static connection. One server will die, the whole system dies, okay? And when you go to complex really computing, that's really never works. So in service-oriented basically computing, we have a lot of lower granularity than here in client-server computing, and the value is on the connectivity, okay? Many system dynamics largely result from interactions among systems. Those interactions really are defined by governance. That's what we say. We govern, we create the federation of federations, really. So for that, we need high-level languages, and that's a kind of summary, basically. So software engineering is focused basically on creating executive codes and objects. That's software engineering. In service-oriented computing, provisioning basically moves those executive codes and objects to service providers. Service providers basically are service avatars. Those are not really avatars. So avatar, physical representation in service-oriented computing are service provider and evaluator, and those are network containers then eventually run those objects inside, in the network. And you are not maintaining any direct connections to those elements. You will find them only by type, by service type, which is unusual, and people don't know really often how to do this. And then you have governance on the top. So governance, basically in the language you will see we use, doesn't have anything directly connecting to object codes or even to service providers. Service provider just expose service type, multi-service type, we call this multi-typing. Where a multi-type, you will find instance in the network. It doesn't exist, that instance is provisioned, and you can basically refer to that instance in governance, what to do with that service. We want, as I mentioned here, so we want to compose executive codes and objects in service network using programming languages with various programming paradigms. So we decided that basically different people have different preferences, and this is basically the choice of the user, consumer that consumes services. The name consumer consumes services. It is not customer that uses custom for him or her design program. And so we just specified basically, it is also for design the language, what is called demogramming gate. And those are basically basic three existing programming paradigms. Those are basically pillars for each paradigm. This is basically domain, usually data, control strategy, and composition. And composition, control strategies, and data is differently used in each paradigm that you have to know if you are really working in computer science, because I told you computer science is the science of process expression, and those are functional processes, those are algorithmic processes, those are object-oriented processes, and we are talking in Sorcerer in service-oriented processes, and they are based basically on those pillars: context-sync, multi-fidelity, and multi-typing. Multi-typing, I mentioned, it is just to compose service federation in the language. Multi-fidelity is real control strategy, and context-sync is basically the independence of individual parameters, so service can work with any data in general, okay? So context-sync really, by the way, everything is what we use context-sync. That means it has ontology. So we maintain ontology for data in the network, we maintain ontology for services, how to find them, and multi-typing is basically one of many possible fidelities because the approach is to have a system of systems. And by changing fidelity, you can move from one system to another. So when we do optimization, you are not optimizing a particular one system. You are optimizing, but during optimization, you create via emergent properties new system. So basically, you look for the best system and find optimal solution of the system that you haven't defined. Because multi-fidelities, they have different range, but you can change all fidelities in the system. That means it is computing completely differently than before. It is different system. So you have like basically a large number of systems in the same program. So obviously, when you look now in the internet that you are using, probably nobody of you believes that internet will survive so long. We need basically the intelligence in the network, and that's the problem with using service-oriented computing, because you need the intelligence in the network. If you don't rely on static connections, how you find your services in the network? You need intelligence, ontologies, I mentioned before, to find basically in the network. Because of that, but the current network basically is called dumb network with respect to what we want really. And in dumb network, basically, it was designed for simplicity inside. You have routers basically, but the assumption was the intelligence lives at the end, which is end user has everything is the whole intelligence at the end user, and the other end you are connecting via static connection. And basically, in dumb network, we just deliver bits. That's dumb. The data will tell you the network where to go. The data at end basically, and that's what is called the end of the end principles. And basically, that implies probably you've heard about 8 fallacies of distributed computing. So if people are not aware about this, because they assume that everything what is true in computing on one platform will work when you use the network. Always fails, and that's the primary reason why service-oriented computing doesn't move, because people don't know how to create intelligence in the network. And I will go faster, but I will tell you that basically the issue is if you have that service avatar, how to make presence or even provisioning in the network. Do you remember? I told you that when we move from manufacturing to service orientation or service economy, the first element is how to provision services. Who will be selling those services in economy? Here, who will be providing those executive codes, objects to you? That's basically service provider, but you cannot talk directly to the service provider, which is not possible with this type of network. That's a kind of graphical illustration while I was talking. So you create basically the consumer governance, and you will see how we do in service modeling language. It is very simple language, frankly speaking, but the infrastructure and that network intelligence is needed, because you operate in global network, and the operating system exists in the network. So this is the major intelligence, how basically a provider starts, which is the avatar for the service, how it registers with registries in the network. You don't know what those registries are. There are special, basically, discovery joining protocols. They do not exist in any type of services. And we were basically on that with Sun Microsystem, which is gone now. Oracle bought Sun Microsystem. It was at the time we developed together for FIPA project, and it was called Genie technology. And currently it is Apache project called River. So if anyone would like to understand how to put intelligence into network, you have to be familiar with River project. And nobody teaches that. I was teaching in my lab at Texas State University. That's the reason it was possible for me to create a group of 28 PhDs who basically worked with me to create the technology. And so this is the operating system services. So kernel and consists of services in the network. They are replicated, usually up to 5. So with 5 services in the network, you have 99 and 9 nines that one always exists in the network. And governance, basically you specify what you want, with help of operating system creates those services, user-defined service federation. And everything runs in those service providers that provision services available at the language level. So that's the concept. And how we have done this, you can define languages in 2 ways, using grammar or meta-modeling. And I had the opportunity to work to represent General Electric for 5 years at the technical committee of OMG, Object Management Group, the group that was designed basically UML. And most people don't know, but UML has meta-modeling hierarchy. This is meta-object facility, then there is UML, then you create your model in UML, and then you have runtime, basically, object model at runtime. And this is the avatar for Sorcerer language that has the same hierarchy. We have meta-service facility, service modeling language that I'm presenting today, basically. Those governance is really a mogram. We have, a mogram is generic term for service-oriented program. Governance is one type of programming for federation, really, for federating those services. And then that mogram basically, with help of operating system, basically bounds to creates the federation, and that federation is just source of runtime collection of objects running in the network, okay? So that was really Genie technology we use here, and for provisioning another open source project, and Sources is also open source project, but only one level. We have like 4 levels used at Air Force Research Lab, so only the bottom is available. The rest is not available. So that's the part basically we have developed over years by analogy to UML, and only that UML is graphical and SML is just functional language. So how, and that's the semantics. That's really, was very difficult over years how to explain to others what is service, and basically finally we got, I don't know, like in past 2 years, the full semantics uniquely specified. So as I told you, this is process expression. That's really what is called services science. That stuff here is called really services engineering. And basically that's here is service software engineering. Basically you write those codes which are provided by service providers. So because it is service-oriented environment, everything is service. So the program that you create, governance is also service. We call them request services. There are operation services, there are elementary services, there are federated services. That's what end user creates, basically, and runs as a federation of providers. And the two operation services, you will see in a moment how they look. Signature and evaluator, and signature has multi-type. That multi-type basically is a service type or service provider, which is a collection of multi-types of service interface types. As you know, not object-oriented languages have service types. Java has basically service type, which is basically interface to classes that have to implement it. So obviously you need to use the service type, but there is no IP addresses, there is no protocols. That is called sometimes technology that says the end of protocols, network protocols. User doesn't need to know about protocols, nothing. Okay. I don't have time to go into details, so let's go. Basically, this is from tutorial exam. Basic, like you have hello world, you have service-oriented hello arithmetic. So you have, oh my gosh, what I did, backward. So you have basically, it is block structured here programming, like you know, in procedural programming, you have basically block in block. This is basically the data. Which provide the scope for inner block, and in that inner block we have another block. So that's the state of all blocks, and basically we have here three services: multiply, plus, minus. Okay, and we assume that there are executed codes. You can just think that plus, multiply, minus is any tool in the network. Okay, they're just explanation. And basically you want to create the governance to run the computation, which is here specified in a kind of procedural way. Okay, so that's the program in Sorcerer that you can execute. Okay, you specify basically the task, this is the name, and that's the signature. And you say, signature, you put the name, that's the operation. That's the operator selector, and that's the interface. That's it, okay? And that interface, as you see, I use here the class implementation. If it is, Sorcerer allows you to build monolithic program that runs on one computer at any time, distribute any service, like here in that case, task is a service, automatically into the network. Okay, the concept is based on the differences I told you between class and interface. So if in signature you specify class type, Sorcerer will create instance for you at runtime to use. Okay, if you specify interface, Sorcerer will find or provision that service avatar in the network. Okay. The provider. You don't need to know where those services are, if they are in the network or not, what computer is used. You can specify you can add to signature deployment descriptor, it will deploy on the right computer, like supercomputer or cluster or workstation, okay, automatically. So we specify basically three services. Those are tasks. And we create the block. Okay, we create block that means do service T4, T5, which is multiply and add. Okay, and then in that block we have outer block, subtract, basically another service from the service. Yeah, okay. Yeah, so this is just basically using a block. We call this block governance. Block has inside the block. We have here not block but job. That's another governance. This is workflow. So block is basically procedural programming. You have basically branching and looping blocks. So we have full algorithmic logic with blocks, like procedural programming. I told you all paradigms we want to have with services. You create a job, which is like workflow. And here also you have job, inside you have another job. It is the same task, but represented as a workflow, okay? You can do the same as a model. Here I use just basic expression. All those, as you see, run in Sorcerer, and really you can execute them in the tutorial that comes with Sorcerer. Here we use basically as a model. Model is basically a kind of functional programming. Okay, this is you use really functional programming just using lambda expressions, and you can mix and match all that stuff any way you want. And this is more interesting. This is the Solar model. This is the optimization. You know, as a tutorial again called Solar model. By the way, it was first time solved in 1996. It is optimization problem. You have like, it looks like, you know, classical definition, but it has two domains. Y depends on Y2, and Y2 depends on Y2 depends on Y1. So you have coupling between those disciplines. So we have one entity discipline, the second discipline, and we have, it is the simplest multidisciplinary problem, and you want to solve that problem, okay? So in Sorcerer, you specify basically, it is, my colleagues decided to call this operator MADO, multidiscipline analysis and design optimization model. Basically, you specify objective vars, output vars, input vars, constraints, basically, and you have basically two disciplines. Basically, you specify couplings, you add sensitivities, it is gradient bands, you run this, and you get optimal solution. Okay, how you do this? You have to specify basically the data, which is context. This is what I told you, we treat context as a kind of ontology. And even in the context, you specify how to run MDA. And MDA here is specified by basically lambda or by a class that implements basically the MDA interface. That's it. So you need the data for that model to be optimized. You need also the task. Like before, only the task specified in the context what is optimizer, what is strategy, and so on. And we run basically and check the results of the optimization. Now those three elements you can put together, and basically, yeah, those are morphers. You don't have time. But at least service discipline. Service discipline is like model view controller. You specify multi-fidelities for governance, dispatcher, and context. Model is governance, by the way, that I showed you for Solar model. Yeah, okay. And dispatcher basically is a task. Context daughter, you put those together and you create basically this. So this is the discipline. And basically you can execute discipline as one task, basically. So what, that's the time to summarize. So I would like to, that you will take away 3 points. Multi-fidelity service-oriented semantics, because each request has multi-fidelities, okay? Multi-fidelities are everywhere in the system because multi-fidelity is ad hoc polymorphism, so it allows you basically to adapt the system any way you want. In order to do this, you have morphers associated with fidelities, and morpher watches what is input-output, and then runtime changes fidelity. So you can go from fast execution, not precise, to high-fidelity model when it is really needed. And yeah, those are basically, those are types of basically transroutine, transmodel, and transdiscipline. Those are 3 patterns for governance. And that's the illustration, basically, what is federation or collaboration. If you have just elementary services, that's basically collaboration. But if you use a hierarchy of governances, this is governance, 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 those are collaborations. So you have basically here service federation that comprises from 6 collaboration and 4 federated governances. So federation is like federated government, like in the States, for example. Okay, each state has own. So let's see, those are states that have own governance, basically. And you can build very hierarchy with, let's say, hundreds or thousands of services in the network. The issue is scalability also for, you know, large-scale system. I'm done. Thank you.
Great. Thank you very much.